I'm Falcon. I'm going to be talking about a new TLS extension that I'm in the middle of proposing. There isn't an RFC yet. I'm sorry. They take a while to write. It'll be short. It'll come out eventually. So, who am I? Well, I'm Falcon. Yes, credentials. I'm a CISP. I doubt anybody expected that. I do consulting work with Leviathan Security in the day. In the night, I'm a researcher on language theoretic security. I work with Sergey Bradis's lab sometimes. Recently wrote a little paper taxonomizing LangSec issues specifically aimed at penetration testers, so if you want to read it, go check out langsec.org. It's really fun. Sometimes I'm a penetration tester. If this is around or in earshot, please don't throw any knives at me until question time. And for a hobby in Seattle, I have a pet #1 crossbar phone switch. If you don't know what that is, relay ladder logic, very exciting. These are the ones we use to blue box. Come check it out. So, what I'm going to talk about is briefly the standards in which this extension works and kind of the landscape into which it fits. I'll give a brief overview of how X509 and TLS interplay and how certificate validation works and what certificates are composed of, just for anyone who isn't intimately familiar with the details so that it will be possible to talk about why exactly I want to do the thing that I want to do. Then we'll talk a little bit about some of the various user stories around how this works and what kinds of things it prevents. So yeah, standards. We have lots of them in the web. TLS developed from a number of other technologies that Mozilla and Microsoft were developing before that. It is supposed to provide a secure transport layer, which is just kind of one step above TCP and one step below HTTP. It is intended to do something that we formally call authenticated encryption, which means that we know who we're talking to, as well as that only that person has the key. Over the years, this property has been progressively more and more violated, and the standardization community progresses in an effort to take it back. So yes, the things that we use to provide the authentication are X509 certificates. The things that we use to provide the encryption are embodied as part of TLS. The way that we used to do certificates, just on background, is by giving everything a distinguished name in the so-called global directory. This shows you how far back this lineage of standardization goes. What I have on the board there is a hypothetical DN. You can see that there are a number of problems with it in that it discloses side channels about, in this case, the propaganda and agitation division in North Korea owning this site. This is perhaps not a real example, but it is sometimes a serious threat. The way that we used to arrange certificates is quite naive, and so it has a proclivity to both disclose information that should not necessarily be disclosed and not encode all of the information that is necessary to make a secure connection with authenticated encryption. The X509 v3 was a later version of the X509 standard that allowed us essentially to create an infinite number of extensions onto a certificate. And I'm using that functionality in this proposal to add necessary information that will act as a canary for us when our TLS connections are being tampered with. The same thing also is how we got subject alternative names, which is why you can have certificates for multiple websites, all of this fun stuff. It is actually quite an extensible, pluggable architecture that is specifically designed for backwards compatibility. The IETF organization PKIX, or the Public Key Interchange Group, I believe. It used to be the standardization body within the IESG to make the standard develop. That's now concluded, and it's being done mostly as an ad hoc process out of random people's internet drafts. The other player in the standardization arena in X509 and TLS is the CA browser form, which sets up essentially not standards, it dictates the policies that CAs issue these certificates by, which will be important to consider later. They periodically decide among CAs and browsers, and they vote separately. CAs want to do this and browsers want to do this. It happens on things like certificate transparency, or something you'll probably be hearing a lot about later, which is the DNS CAA records, or something else you'll probably be hearing a lot about later because it's almost done, is TLS 1.3. It is a democratic organization that just decides what CAs are going to do and which ones are going to be accredited by whom, and establishes the route that ships with browsers today. So yes, the standard is designed effectively for extensibility and backwards compatibility. This is very important because it allows us to just kind of add things to the protocol without interfering with existing protocol users. TLS is essentially the same way. Newer versions of TLS implement an arbitrary extension set, and as well as this, the version field is such that a host running SSL v2 or 3 should be able to understand and reject a handshake that is intended for a TLS 1.2 implementing host. It also causes us to have identifiers assigned to every protocol version, suite, encryption scheme, what have you, in order that we can implement features like this. So, I'll keep talking about X509 for a little bit because it's important. Essentially what a certificate is a signed blob of bits that says whoever can sign challenges that are verifiable against this public key with this algorithm is the named entity. So what this means is I generate a private key, I send the corresponding public key to a certificate authority who says, I am pretty sure that the person who operates this site is also the only person who has this public key. And with that assertion made, anyone who then can sign a challenge that is a piece of key material with that public key can say, and you are talking to this website if you encrypt against this. The assertion is essentially made with the strength of the issuer, so that is your certificate authority. The issuer adds many things to this document. It says things like, here is the point where I distribute my CRLs, check here for revocations, check there for OCSP responses. This key may be used for certain things. You can use it to encrypt website connections, but not say to sign code and emails. Because it didn't want to attest to you as a developer, just you as a website operator. It says whether or not the key is a sub-CA allowed to make attestations on the CA's behalf. Unsurprisingly, this field is almost always no. It also encodes information about how the CA verified that identity, and it further encodes an expiry date in order to force you to continue paying them. Actually, to force you to rotate your keys, but that's not how it ended up working. And it also includes information like if you want the certificate transparency logs to be sure that we were on the up and up when we were issuing this one, look here. I'll show one in a moment. In fact, I'll show one now. Let's briefly look at the certificate for Facebook.com, which includes all of the modern features and makes a very, very, very good example. We'll pay attention to the concept of extensions, and the purpose of this exercise is just to look a little bit at where this extension will go. Oh, I should probably blow that up a little, shouldn't I? Maybe I should have taken his advice. Control 1+, that's why. Let's just do that. I'm sorry. Yeah. What does it want? 1260 by 9? I can't do that. 16 by 12? There we go. Yeah, don't power it off. It's good. Oh, no. Okay. Crap. All right. How goes? Warming up? Oh, I'm sorry. Okay. So as that goes, essentially what I'm going to be talking about is how these turn into just a random collection of signed assertions with increasing degrees of complexity. There are some issues in this that I like to test for when I'm conducting penetration tests. There are a great deal of embedded URLs in this, which a badly configured validator will happily just, XML forced browsing style make get queries against. Oh yes, I'd love the CRL for this certificate that isn't even signed by a valid CA. it's happened. I suggest that you look for it. They won't usually authenticate those requests, but they will at least make them, and if there's something that has side effects on GET requests, you kind of get a freebie there. Should I go down and help? We're coming back, okay. What else can I talk about this without actually showing it to you? On the video feed, just not on the projector. Okay, okay. Yeah. The format that these certificates are encoded in is called ASN.1. It's a format that comes from telephony and is used quite heavily in SS7 networks. It kind of sucks in a number of ways, but one thing that is nice about it is it allows you to just create arbitrarily long sequences more or less for free. I don't know if that's legible. I can read it from here at least. So you can see that, for example, we can put very large blobs into these certificates. There's something here, the certificate transparency pre-certificate SCT is literally just a series of signed timestamps and signatures that say the following list of certificate transparency logs have attested that this certificate was encoded into them. And you could have 4 of them, or you could have 20 of them. It's all just a question of how much bandwidth you want to use every connection that you establish. All of these things, from the subject down to which extensions it supports, which CA signed it, the key for the subject, all of the various websites that this is for, the key usage, all of these things are signed by the signature blob at the very bottom, which then is encrypted by RSA into the certificate, and that is how they are verified. You check the RSA signature from the CA certificate over this SHA-256 blob, and you know that it's real. So that gives us a very strong cryptographic assertion that is rooted at the time that the website is set up. And this is very important. It is a request by the website administrator to say the following things about this key as it identifies this website. Some of these extensions are marked critical, like, for example, this X509 key usage extension. This is also important. I do not mark the extension that I'm proposing here critical so that it doesn't cause backwards compatibility issues. The meaning of critical in this context is if you don't understand this extension, then you don't know what the certificate means and don't use it. It is a way to kill assertions that would be confused for other things by a client that is not aware of the extension. And so in consequence, we don't mark things critical if we want them to be backwards compatible. And that is largely all that I wanted to say about dissecting the certificate. We can move on. Now, does this still work? That's the real question. Oh, well, all right. So the other thing that I want to do is switch back again and dissect exactly how the negotiation process works in Wireshark. We'll chat briefly about a failed and a successful negotiation, and then I'll get into talking about how we're going to use this standard protocol environment to make an incremental improvement that will kill a poodle attack forever and without breaking backwards compatibility. So let's look at this failed SSLv3 negotiation. This will also help to discuss a little bit about what happens when a negotiation succeeds or fails. Oh God, I hope that's readable, but if it's not, I'm not going to try changing the resolution again. So this sequence is very short. What it is the host makes a TCP connection in. Sorry about the eye chart. When we want to decode these things in Wireshark, by the way, if you have used a non-standard port, it will actually play dumb and not bother to tell you what it is until you tell it this is actually SSL. And then it'll dissect. So the way it starts is we establish a TCP connection with a three-way handshake, as you're familiar with, and then we start with the client hello. The client hello is a little document that says, this is the protocol that I'm trying to support. It's TLS 1.2 if you can't read it. It also says things like, these are the cipher suites that I support. I'm the client. I get to assert, hey, if we want to talk, let's use the following list. Sometimes it includes garbage ones, which is an extension that somebody made up specifically to protect the kinds of backwards compatibility that I was talking about. One of the most dangerous things about these protocols is you can't simply reject things that you think are invalid or suspicious. You do effectively have to accept them if you want interop. This isn't a very good way to do things as far as I'm concerned with my Langsec hat on, but it's the world in which we live. It asserts which compression methods we're allowed to use, in this case null. And it communicates what kind of extensions we support. If there were a client certificate, it would be conveyed in this list. The server comes back and essentially says, well, I don't really know what you just said, but I support SSL v3, and here's my SSL v3 version of the handshake. If you can see it, the protocol version there is v3. It sends some random data, key material. It sends its certificate, and which is, again, bandwidth constraints. Probably why Google.com does not include the CT transparency information. And anyway, it includes its full certificate, and then also, eventually, somewhere down here is the server key exchange message, which says, I have these elliptic curve parameters, and this public key that I generated for this session because we're using ephemeral Diffie-Hellman elliptic curve, and a signature with my RSA key from the certificate or my elliptic curve key from the certificate over that key that I just exchanged. That is how the authenticated key exchange protocol works. Up until this point, this is the only signed message in this TLS exchange, unless there was a client certificate, and then there may have been before, but it will probably come after. This is the only thing that is signed. Everything else about this message is completely mutable. And furthermore, everything else about the client hello message that we looked at earlier is also fully mutable. So, at this point, we were just about to negotiate SSL v3. My client for this did not support SSL v3 because we were mitigating the poodle attack and turned it off. And so in consequence, it says, well, all right, I'll just send the lowest version that I speak, which is TLS 1.0, and I'll tell you, no, this is not going to work out. Our protocol version is too low. I'm going to send you an encrypted alert that says, we're done here, we can't talk. And then the TCP connection is closed, there are fins, resets, all these things happen. So that's what happens when a SSL connection fails to be made because of the negotiation failure. Your browser will usually display some kind of cryptic error of this site can't be talked to. When it succeeds, because we established TLS 1.2, we do a very similar thing. I have a client hello. The client hello includes just the same records that we included before. My protocol version is TLS 1.2 that I'd like to talk to you. Here is all of my key exchange material and a list of all of the things that I support, including all 14 supported cyberspaces. Then the server sends back a hello. Why, yes, I also speak TLS 1.2. Here are all of my extensions, including, my server name, the cipher spec that I actually am selecting. Each version of the protocol ends up being slightly different. In this case, the server replies with its server hello. They negotiate what the protocol is going to be. And then once they've decided things like what the signature scheme is going to be, then later the server sends in a second message what the certificate is. This kind of thing allows us to, say, use both an elliptic curve and an RSA certificate. It's handy. In this case now, the server sends its certificate, server key exchange, and server hello done, which means that it sent you a signed assertion of its key like we were talking about before. The client says, why, yes, I agree to that key. Here is my half of it. Now the key exchange is done. When you have both of these channels of communications, it doesn't actually matter what algorithm you're using. That will work for any. As long as both people are aware of what algorithm they're using, then they can negotiate keys in this way. Change cipher spec to start encrypting. They haven't started encrypting until after this packet, and then also send me some other data. After this point, everything is encrypted and signed. Before this point, almost nothing is encrypted and signed. And so the way that many types of attacks on TLS work is your attacker will do things like drop some of these protocol messages strategically or mutate them because they're man in the middle, and modify what happens during this negotiation process. I submit that this is an extremely bad thing. I'm sure I'm not alone in that. So, now that I'm done switching back and forth, and Windows is questioning whether I'm licensed because I use a separate user account for this, let's talk a little bit about some attacks. An attack. You might be familiar with the poodle attack. It's fairly well known for being difficult to exploit because you can only exploit it if you're man in the middle. This is becoming a serious problem as time wears on. But it was published as an academic effort by some researchers at Google. And they started off by saying SSL 3.0 is an obsolete and insecure protocol. For most practical purposes, it has been replaced by its successors, TLS 1.0, 1.1, and 1.2. But many TLS implementations remain backwards compatible with SSL 3.0 to interoperate with legacy systems in the interest of a smooth user experience. Quote, that is essentially the problem statement in a nutshell. Our solution to this point has been given by Sans. Sans says, what should you do? You should disable SSL v3. You really have no choice. It doesn't matter if all of your people that you're trying to convey your website to for e-commerce purposes only support SSL v3. You just have to disable it. This isn't going to be a patch now scenario. Obviously. I would have never guessed. They're right. We have to turn off SSL v3 in the current landscape. We simply have left ourselves no alternative. We will also be finding that we have to do the same with TLS 1.1 as we have with TLS 1.2, and in due course, we will no doubt find the same problem with TLS 1.2 and TLS 1.3. It happens, software doesn't age well, you have to update. Our old strategy of negotiation is not working well because of things like the Poodle attack. If anybody supports the bad protocol version, then everybody supports the bad protocol version. Sadness is ours. The red arrows represent a possibly lower level connection than would have been negotiated by fully compliant hosts, which support everything absolutely the newest and have all of the modern mitigation techniques. The vast majority of arrows are red because if there is even one legacy participant in the conversation, then we don't really have a good alternative. So in the current landscape, the red arrows would probably represent SSL v3. The green arrow probably represents TLS 1.2, but I'd like to just mention and kill right now, this is timeless, and I could probably use the same diagram 10 years from now to talk about other protocols. Unfortunately for us, we're kind of doomed. Over a year after this was disclosed, this Poodle vulnerability, Census did a census, and they discovered that still 96.9% of the Alexa top million sites that supported TLS still supported SSL v3. So much for Sans advice to just disable it. That worked really well. And also please rip XP out of your environment, patch all of your systems right now, never reject a software patch at all. You just shouldn't. No, go, go, go. Don't worry about your change control board. I know. Does anyone want to cheer ITIL? Hey, I have a better solution. So, I know, my stats are old, but I actually ran them again yesterday morning and I found that still 12% of sites continue to support this here in 2017 from this issue that was disclosed in 2014. So the solution that we have right now of disabling things and updating everything post-haste clearly is not working. Most of the sites that were in this, actually, maybe I shouldn't have blamed Russia because it turns out that actually they were almost all Chinese sites, Baidu, 360.cn, things like this. I submit that there's a reason for that. It seems to be uniquely hard to get rid of Internet Explorer version 6, which technically does support TLS 1.0, but you have to turn it on, and TLS 1.0 is vulnerable to these sorts of things anyway, so no one bothers. If you want to replicate this study or a similar one at any point in the future, you can use this lovely site census.io, which essentially scans the whole internet showdown style, but instead of gathering just strings, it gathers a little bit of metadata and statistics as well that are useful to academics like me. If you run those two queries, I'll post my slides later, and just make a division among them, then you will be able to get this number and see it decline over time. You can also check for support for all sorts of other things, including SCADA systems that are online as a proportion of network hosts on the internet in general. It can just answer these queries for you. It's lovely. So, I think we need a better solution. I don't think that what we're doing is working right now, and we need to just tear it down and start over. So back to my outline. Now we're done talking about background, and we can talk a little bit about what it is that I actually am proposing to do. Then we'll talk about how this can be one of the building blocks that helps to mitigate TLS interception by people who enjoy making state-level internet censorship. We can talk a little bit about how this prevents some kind of so-called nation-state level attacks on the internet. And we can also talk about how it enables defenders, even government defenders, to help keep better control over their environment and prevent system administrators from making configuration errors. If we can't just get rid of SSL v3 and burn it to the ground, What if we just sign the negotiation blob? Well, unfortunately, we don't. If you remember what I was dissecting in Wireshark earlier and were able to read it, you'll notice that we don't start signing anything until very, 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 very late in the TLS exchange. And the reason for this is because until that point, we haven't decided what algorithms everyone supports and what key we're going to use, and we just can't. It may be possible to do this sort of thing by piecemeal, but that would interfere with things like the possibility of supporting DSA, RSA, and elliptic curve in your TLS certificate. So we don't just sign the negotiation blob, and we can't, and that solution wouldn't work anyway, and it is far too deep and buried into the extensibility machine to actually be reliable. So, remembering how attacks like Poodle work, if the vuln is in key exchange, how do you sign assertions with a key? You just don't. But we still need to sign it, and we still have a trust root, right? So why don't we put it in the certificate? The certificate is a necessary part of the TLS connection. It's signed so that the attacker can't modify it, and it carries the same information that we needed to sign as part of the negotiation but couldn't because we have a key. And the good thing about putting it in here is that we can actually sign it multiple times for every certificate that we have and need to use. So it doesn't interfere with the process of negotiating which certificate we're going to use. It doesn't interfere with the SNI process, which is something that triggers a certificate selection to occur. I didn't explain it before I was going to. In SNI, what happens is during that client hello, you say, and by the way, I'd like to talk to this particular domain. I want www.google.com versus google.com, and the server is free to then select whichever certificate it wants to send back in its server hello or in its server key exchange messages. And so there's quite a lot of extensibility built into this, and we would actually need a different one of these certificates for every single such configuration that we intend to support. Remember that the certificates are generated to your specification as the site operator and certificate authority. It's a collaborative process. The two of you decide together what you're going to request and what you're going to permit to be signed. They're collections of assertions that the website operator authorizes about their site. Before I alluded to the CAA extension, it is called Certificate Authority Authorization, if I recall, and it's a new one. It is mandatory as of a few months ago for certificate authorities to support it. It allows the site operator to specify the following certificate authorities are allowed to issue certificates for my site. No one else may issue certificates for my site that are valid. And by the way, also potentially here is my own certificate authority account number, so that even if you know who my CA is, you can't social engineer them into, or very easily social engineer them into issuing a certificate for my site. It's optional for website operators for obvious reasons. I expect it to become more and more of a thing in the future. The CA has various rules about what kinds of certificates, what kinds of assertions they will allow. For example, most CAs will not sign certificates with completely random OIDs in them that they do not understand unless you talk to them first. Most certificates will not issue most certificate authorities will not issue certificates that have odd types of extensions. Say, this is a remote desktop code signing and TLS client authentication certificate. They have rules. The rules are documented in the policy sets. They're extremely large. If you need something to go to sleep with, I highly recommend reading one. So with that said, the thing that I am making looks a little bit like this. In ASN.1, remember, we have large sequences identified by large amounts of numbers that are OIDs. You can just make these. If you can get one assigned, you can just generate a new extension that has a specific meaning. And it is guaranteed to be unique. Everybody who goes before you is not allowed to have used it. Everybody who goes after you cannot use it unless they know what it means. That's why certificate authorities won't just sign random crap. They have to understand each of these OIDs that is in the certificate. So this one in particular is a very simple one. Much like the list of certificate transparency records, it basically says, I have a sequence of various policies that I attach into my certificate. It says, these are the TLS protocols that you must support, i.e. TLS 1.2. These are the TLS protocols that you must not assert support for, SSL v2. And on for ciphers and compressions and anything else that turns out to be useful to add. We can create infinity of these because remember, when a browser doesn't understand one of them, it will just ignore it because they're not marked critical. Each of these things are just a sequence of the protocol identifiers, so it's very easy to maintain. In fact, it's zero maintenance. And the idea here is that we can use this assertion as encoded in part of the certificate and signed by the certificate authority's key. Remember that when we issue a certificate, we also know that the website operator, through our verification process, requested this specific certificate with these specific things in it. And we put the canary here. I'm sorry, I made another eye chart. What this says is there's a client hello packet that we talked about before. It sends its version, its cypherspec, its crypto support, all these things. The server sends back its own version negotiation and cypherspec and things like this. And then there's a key exchange that goes on. We put the canary at the very bottom of this, at the end. And so what happens is, after all of the negotiation is done, we now have an opportunity to say, is what actually happened consistent with the assertions that were made by the site operator and their certificate authority, and that was conveyed to me? And the trick here, the crowbar that we use to make this forced, is that without the certificate, you can't prove identity or ownership of the site. You need the client to trust you in order to interfere with this process. And so you can't simply do the old poodle trick and like just drop random parts, because the entire certificate is signed, and when you begin chopping things out of it or suppress the certificate entirely, it just won't be verified, as we know. And so what happens is the user agent says, well, wait a minute, we for some reason are speaking SSL v3 with like RC4 export, and we know that the site operator said that they support TLS v1.2 and AES 256 GCM. What happened? Maybe we should send back an encrypted alert and suppress this, because clearly something has gone wrong and we're likely being tampered with, and this connection is not private. So now I'll get into a couple of user stories as to exactly what we can use this to prevent. At this point, I think that everyone understands that there is a deep problem with TLS inspection. A lot of people feel that they have regulatory compliance reasons why they need to have a TLS intercepting proxy that renegotiates connections. These lovely people published a paper at NDSS about, I think, 3 years ago now. No, I think it was this year. Anyway, the paper is called The Security Impact of HTTPS Interception, and it basically says, in almost every case that we surveyed, we found that the TLS intercepting proxy negotiated a weaker protocol in cypherspec than the clients behind it support. And we found this because we fingerprinted the browser user agent, and we know what that browser supports and what operating system it's running on and what that operating system's crypto layer supports. And yet, for some reason, what happened is not actually consistent with what is supported on either side. That implements a weaker version of the property that I'm implementing here today by encoding all of this extra information in the certificate, because it's not cryptographically verified, and the user agent can be subject to tampering if you have compromised the TLS connection. But nonetheless, in this case, they were able to discover that antivirus proxies and things like proxy SG had a proclivity to reduce the security level, not only by creating an additional point of decryption that can be attacked by attackers and by subsuming the client's responsibility to verify certificates, but also by supporting a weaker protocol set than the client supported and being updated on the slower update cycle. It's really just not a good thing. Sometimes government actors use these too. The graffiti I just like. It actually has nothing to do with this, but it's becoming a severe enough problem that we're actually now seeing graffiti in places like Turkey that literally just says DNS 88884221. So maybe we should help provide technical solutions to these problems. This can be part of, it is not a complete solution, unfortunately, to the censorship issue, because obviously if the client trusts the censor's TLS certificate, then they can just make whatever kinds of assertions in the certificate that they want. But in a landscape that has other standards at play, and I didn't go over them all because I didn't want to bore you senseless, but I'll talk about a little of them now since we have time. There was a proposal a number of years ago to introduce a new DNS record called TLSA. And this DNS record is very cool. It cuts the certificate authority out of things entirely and allows you to just put your certificate in DNS, pin it, and say, the operator of the site, which is the same person who's allowed to change the DNS records, obviously, and the registrant of the domain says, this one is the TLS certificate that identifies as web server. It works great, except when you remember that TLS is actually not authenticated unless you use DNSSEC, and support for DNSSEC is in such a sorry state that we can't actually use this right now. Maybe someday. But if someday we have TLSA, then we can actually use this to convey from the DNSSEC route what protocol versions we're allowed to support. We could also directly add this to the broader mechanism under which TLSA falls, which is called DANE. That mechanism is also used to do things like convey SSH keys for various things and policy statements and all of that. Again, it doesn't help if you trust the man-in-the-middle CA. If there's a trusted retermination, all bets are off, and you just have to know that you're being interfered with because you installed the malicious root CA. So essentially, the diagram of what an intercepting proxy that is intending to commit fraud or censorship would have to do now suddenly looks like this. The web server speaks TLS 1.2, the connection has been degraded down to TLS 1.0. But in the meantime, the DNS traffic says, well, this connection is clearly being degraded because, you know, the TLSA record implies through the certificate's signed TLS policy assertions that we should be supporting better than this. And also we can use certificate transparency as a back channel to convey information about what is signed into valid certificates for the site. You can simply look up what certificates are valid for a site in various certificate transparency logs. There are many of them. It's itself conveyed over TLS. It would be quite a chore to interfere with. And so while this doesn't actually, unfortunately, prevent this type of TLS interception attack, in the broader landscape of all of the things that we want to do in the internet, it would make it astonishingly difficult and a huge development effort that would be very expensive to do, and I submit that this will reduce the number of people that do it. Also, when we're being spied upon and somebody is, you know, making, thank you, I was hoping someone would catch that, when someone is dropping all of our attempts to negotiate nice protocol suites because they'd like us to use SSL v3, we actually have a little bit of a recourse here. There is already a mechanism that does this. It is perhaps less robust than the one that is here proposed. So in this case, at the end, once we see, well, in the server hello that's going back, we have SSL v3 and the certificate, which by the way includes an assertion that says that the site supports TLS 1.2 or 1.3 or whatever version we're on right now. It'll send back an encrypted alert saying, hey, no. The other mechanism that does this is called SCSV, or TLS fallback SCSV. It provides some level of downgrade protection by adding a new cipher spec to the negotiation. It's supposed to be used, it's specified in this RFC. The way that it works is when you found that you could not negotiate a higher protocol version because it was being dropped and you just got no replies, you include this TLS fallback SCSV cipher spec in your client hello, just to alert the server of, by the way, I have downgraded in case you didn't know, and the server is supposed to say, oh, you shouldn't have downgraded, let me fix that for you by not talking to you anymore until we're no longer being watched. Did I mention that the client hello is not signed? Somebody who's intercepting this as a man in the middle can often simply strip out this extension, especially if you've downgraded to an older protocol version like SSL v3 in which that assertion is just completely not signed. I understand that there are some proposals to sign it later, which are good, laudable proposals. But for so long as we have to maintain backwards compatibility, any changes that we make to the TLS protocol itself that are intended to provide this functionality will continue to be vulnerable to an attack like the one that is pictured. And finally, my last user case, which is a policy extension. Remember that the certificate is definitely something that is agreed upon by the client and by the certificate authority and the website operator. So what that means is that the certificate authority has some kind of say in this. And although what happens is that site administrators often accidentally configure things to try to make them work and don't realize that they were supposed to type the following magic words, you know, here's the correct miles-long cipher specification of the month, and by the way, remember to type something like SSL protocol minus SSL v3 into your Apache config and restart your web server. I kind of understand why they keep screwing this up and why we still have so many sites that support these things. If you look at beyond the Alexa top million, you'll see actually a small increase in the number of sites that support SSL v3, and they're just badly configured small sites, perhaps test endpoints, I don't know. But yeah. Well, I mean, why do they have such a hard time complying with FIPS? That's probably why it's complicated and difficult, and there's no central policy mechanism that is effective at forcing them to do this beyond scanning and filing change requests on them. So, PKI can help us out with this. If you are DoD root CA2, you can simply say, no, if you want a certificate that doesn't assert that you support TLS 1.2, you're going to need some kind of authorization for that. And so suddenly, Now, although you can misconfigure your web server, the fact that it is misconfigured will become obvious because your configuration does not match the rule set that was specified in the certificate. Either you support things that are prohibited or you do not support things that are required, or the negotiation results in the negotiation of something that is prohibited, or the not negotiation of something that is required and preferred. All of those scenarios encompass the totality of what can go wrong when the TLS negotiation is tampered with. So, all that you need to do if you are the CA, and you want to prevent people from misconfiguring their websites because you're an enterprise CA and you manage them, you just have to add this assertion to each of the certificates that you sign, and your problems will go away as soon as browsers begin to support functionality like this. Again, gonna write the RFC soon. Yeah. So what's next? My plan is to write an RFC to finish patching this and finish patching this into OpenSSL, so there's proof of concept, and it's my hope that people will take it up. At that point, I'll be very noisy, and it would be good to have some evangelism if somebody knows a browser vendor, because I don't. And I also intend to potentially prove the security of this protocol using a little thing called Tamarin, which is a tool that we use to prove whether a cryptographic protocol actually makes the assertions that it is intended to make, and whether all of the state transitions can possibly lead you into a state where you didn't want to be, and publish that academically so that further weight gets behind it. But I figured that I would give a preview of what happened, or what I'm intending to do here. So, that's all I've got for you. A little under, but feel free to ask me questions about how this whole thing works, or this technology in specific, or our general plans for this. Yeah, follow me on Twitter. No questions? None at all? Hey.
Let me bring you the mic, sir.
So you're going to assume that when the crypto downgrades or upgrades in the server configuration, then I also do need to get new certificates.
No. No, you don't. You should. You should. And people actually rekey. The Let's Encrypt project, or CertBot, which you're very familiar with, I'm sure, has, no, I know you wince, but it is part of a kind of new guard of kind of DevOps things whereby it's actually possible for a shell script just to get the certificate reissued. It's a very, very casual process, unlike what it once was, where you used to have to sign documents and mail things off to people and send copies of ID. So it's not as much of a chore. In fact, if you're using Windows and Enterprise PKI with Active Directory Certificate Services, the server just automatically reissues these certificates constantly against the new template. And so it's actually not as hard of a problem as you think to reissue certificates constantly, but you don't have to with this extension because I didn't mark the things critical, and it's simply an assertion of policy. It must try to support this, and it must not support that, but it doesn't say things like, and the negotiation must result in exactly this. If suddenly in the interim, while you are in the process of renewing your certificates and haven't gotten to it yet, you decide that you want to enable a new cypherspec or TLS 1.4, it would not actually interfere with this because the browser would say, well, it did actually assert that it supports all of those things, but we prefer this other third thing that's not even mentioned in the policy. Let's go with that. Go ahead.
So my point was that if, for example, in future 1.3 is found to be vulnerable, and I disable this in my server configuration, but then the attacker can do the downgrade, knowing that 1.3 is vulnerable, while I still have this in the certificate.
Yes, well, if you don't update your policy or you don't use this extension at all, then you will remain vulnerable.
And also, I do avoid the Let's Encrypt as much as possible, because it's mostly used for, well, not mostly, but quite a lot of use for malware. And I tend to discourage people using it for that reason.
Yes. I know, it's awful. We have the same problem in many other concepts of PKI, and it's something that, since we have a little bit of time, I might as well call out, because it's a conversation that I end up having with a lot of people, both my clients and other people in the industry. You're not wrong. It's just a question of what we're signing, and we need to be very conscious of what we're signing. For example, code signing certificates do not make code trusted. They are not an audit. They don't sign that this is not malware. They sign this entity, which we verified to some small extent as to ownership of a particular legal name at most, is the person who decided that it would be a good idea to attach this signature to this thing in their build server. Similarly, with a website, certificate authorities have this constant intention not to issue certificates for paypal.mysite.com, which I personally feel is, while a noble effort, potentially misguided. The assertion that this person is allowed through DNS to use that domain name is not an incorrect one. And we should probably stop relying on certificates as an assertion that something is not malicious entirely, because they really aren't. You're not wrong, though. They are definitely enabling malware authors. We just have to, much like the spirit of this extension, change our behavior. I submit. Is that all? All right. Thank you.